taking the time to join us today. We very much appreciate the opportunity to speak with you and look forward to a healthy discussion. Over the last several months, we at Mechanical Sales Midwest have met with dozens of building owners to determine how best to prepare their buildings for reopening. And through the course of those conversations, we've become all too aware of all the conflicting information out there, making it difficult for many owners on the proper course of action. To that end, our goal today is to provide information from accredited sources on what we know about the spread of the virus, discuss the various industry-approved options, and how best to implement them. To lead the discussion for us today, I am joined by Dean Saputa, Vice President of UV Resources. Dean has been working in the HVAC industry for over 3 decades and has specialized in air and surface treatment and cleaning technologies. He is a contributing author to the 2019 ASHRAE Application Handbook, has served on several technical committees, and contributed to the ASHRAE position document on filtration and air cleaning that many contractors and engineers rely on for guidance today. As one of the leading experts on the topic of clean air, he has been extremely busy this year, and we're very happy to have him join us. With that, I'll hand it over to Dean.
Great, Tyler. Thank you so much, and thank you everybody for joining us today. My main focus today is going to be on ultraviolet lights, but feel free to be able to ask some questions. I'm also on the ASHRAE Epidemic Task Force regarding filtration and disinfection, so maybe I can give you some ideas from there too. But we're going to concentrate mainly on UV lights and mitigating disease transmission with germicidal UVC. And feel free to go ahead and put something in the chat if you have a question. Hopefully I'll get to be able to answer all those before, maybe we'll just do questions at the end. But thanks again for BOMA and also for Tyler for hosting me here today. So the very first thing I like to do is to go over just a little bit about what the basics of ultraviolet are, the basics. So basics of germicidal UVC, infectious diseases, mainly can we inactivate or how do we inactivate airborne pathogens? Applications such as airstream disinfection, what we call in-duct or on-the-fly applications. Upper room air disinfection, you may not be that familiar with it. It's been around for 80 years, but we haven't seen it much here in the US. It's mainly been used in other parts of the world. But we're going to show a couple of pictures and some talk a little bit about that. We don't want to get away from one of the main things that UV is used for, which is going to be taking care of coils and surface cleaning. And then make sure you're aware of the ASHRAE position documents, American Society of Heating, Refrigeration, Air Conditioning Engineers, and then open it up for some questions. So from a basic standpoint, when we look at the electromagnetic spectrum, and it has all of these rays in here from cosmic rays all the way to microwaves, pardon me. And we have the visible light spectrum, which is the violets to the reds, or colors that we can see. Right above that spectrum is the ultraviolet spectrum, and it's divided into these 4 categories: UVA, B, C, and a category called vacuum UV. And they cover 100 nanometers to 400 nanometers. So it's a really broad spectrum. When somebody says UV, UV's covering a lot of different things. So we're going to kind of dissect it down a little bit. Now the sun produces all of these different wavelengths. UVA penetrates through the ozone layer, UVB, part of it comes through, but UVC is rejected off, and we do not have any UVC penetrating down through the ozone layer. So when we're talking about UV, we're not talking about UVA, which is usually the sun tanning bed lamps or causes wrinkles, or that's something different. That's UVA. UVB is the skin health or cancer causing form of UV. So again, these are the 315 to 400 nanometer areas, 280 also. UVC covers the 200 to 280 nanometers. And I'll always like to, on this slide here, show that there are parts of the UV spectrum that can generate ozone. So I'm going to go back just one slide so you can kind of see that here. So when we talk about germicidal ultraviolet lamps, we're talking about the wavelength of 253.7 nanometers. For ozone to be formed, it's under the 200 nanometers. So anything down here in the vacuum category. So 185 is the predominant line for ozone. So when we're talking about ultraviolet lamps for air disinfection, they'll have no ozone production at all. You can use lamps that have ozone production for water treatment. So when you're doing water purification, they'll have ozone generated out of that. But there's no ozone coming out of germicidal lamps used for the air side of it. So at the 253.7 nanometers, or as again, we rounded out to 254, what's happening is that wavelength is breaking through a cell wall. And as it gets into that cell, it starts to damage the nucleic acids and proteins, making it incapable of reproducing or being infectious. And we cause these things as you go into the double helix of the DNA. We start to break apart the DNA strands and cause these things called thymine dimer lesions, breaking them apart. So each product has a different susceptibility, but in a quick nutshell, the 253 works through the cell wall, permanently damages DNA, can no longer reproduce. To look at the DNA response to different wavelengths, DNA starts to respond to a wavelength of 230 nanometers, and it starts to max out at 265. So that's going to be the highest response rate from a DNA. And then it drops back over here into our UVB spectrum. So this is your curve. So the maximum cell damage happens at 265. Well, the germicidal lamps used for air disinfection are going to be at 253.7. So very, very close to that high spectral line. But we're here talking about infectious diseases. So let's talk a little bit about what's currently out there, the coronavirus. Coronavirus, if you look at that as comparison to influenza and SARS, what you see is they're very small. This is the airborne side of it. There's the larger droplet nuclei that lands on surfaces, but on the stuff that can stay airborne, it's very, very small, 0.11 mean diameter in microns. So this product can act more like a gas than it does a particle, so it can float around for quite some time. If you look at some of the studies that MIT did regarding a cough can travel as far as 16 feet forward. A sneeze can go up to 26 feet. And then these very, very small little particles can stay minimum 8 to 14 minutes up in the air. So we think about our HVAC systems in our buildings, and we have an occupant in one room who may be infectious, and the large stuff drops out onto the surface, but this very small stuff starts to get sucked up into the HVAC system. And if we're designing, let's say, an office building, which many of you folks have office buildings, we're designing around 6-8 air changes an hour, which means about every 7.5 to 10 minutes, that air is brought up into the HVAC system and recirculated back to other zones within that building. So it is a vector of transmitting very small particles, and we've known that because of tuberculosis. Tuberculosis has been around for a long time, so we certainly know the vectors of how that is transmitted. And this is very similar to the same transmission rates. ASHRAE was one of the very first folks that said that, yes, this can be done through the HVAC system. So when you look at
pathogens have different susceptibility to ultraviolet light.
Meet myself out. I guess I got a
here from the left to the right.
Give me 1 second here. So some things are harder to inactivate, and some things are easier to inactivate. So if you look at a Aspergillus niger, one of the hardest things that UV is going to be able to inactivate, it takes quite a bit of energy. It takes about 333,000 microwatts per second per centimeter square to get 99.9% inactivation. The reason I point this out is that's usually something that's not growing inside of it's growing inside of a cooling coil, it's growing in a drain pan. It doesn't necessarily mean that it's flying by in the air. So certainly something that UV can take care of by just hitting it constantly in a drain pan on in a cooling coil. Smaller products like your tuberculosis, for example, or even a coronavirus are much more susceptible to UV, and it doesn't take as much UV energy to inactivate that product. And so these other products can be airborne. So it doesn't take very much at all. So the one we're obviously talking about is coronaviruses. If you look at coronaviruses, Dr. Wally Kowalski wrote a book called Ultraviolet Germicidal Irradiation Handbook, and he did a really nice job of being able to summarize all the cited studies on how much UV energy it takes to inactivate products. And so what you're seeing in the background is these are what's called the rate constants for viruses. There's also bacteria, fungi, and mold. He has those as well in there. So these viruses here, they're either surface, water, or air. So we know exactly how much energy it takes to be able to inactivate something. So we call it the K value, or you may even read in other things called the Z value. In this particular case, a coronavirus has this value of 0.35120 joules per meter squared for us to be able to put that much UV energy into a space to be able to inactivate it. So when we're talking about things in our applications for our buildings, we're talking about 3 different specific applications. We're talking about applications for airstream disinfection, where we're trying to inactivate something flying by in the air, upper room, and then also just being able to maintain systems for energy efficiency. So HVAC, surface, and coil cleaning. In the air disinfection, there's a little bit more math that goes into being able to calculate out how much UV you need to inactivate a certain product. Turn that off. So to be able to inactivate a certain product. So we need to know a little bit more here in this area. We need to know what the height, the width, the length of the chamber is, or the plenum, or the coil section. We need to know airflow. We need to know reflectivity. And then we come down and say, what's our removal rate? How much do we want to be able to take out? Is it going to be 90%? Is it going to be 95% or 99%? So you can use this math to be able to figure out exactly how many lamps you need to place in the space to be able to get the removal rate that you're looking for. So what you're seeing here, this D90 value, is the dose 90 for how much it takes to be able to take out 90% of that on a first pass. So we're sizing systems all the way up to 99.9% first pass inactivation. So it's things like simpler way to look at it is, let's find out what the rate constant of the pathogen that you're looking for. Let's know what the airflow, temperature, relative humidity, that gives us the exposure time, height, width, depth, duct reflectivity. And then the last thing we want to make sure that when we're modeling, that we model a system at the end of the life of the lamp. So one of the things that we do know is that if we are going to put lamps within a cavity, like you're seeing here, this is the downstream side of a cooling coil, that we want that lamp to give us a 360-degree distribution of energy. We don't want to inhibit it at all. We want to be able to let that energy go all over that cavity or all over that plenum space. So we want to be able to get a microbe as it's in the coil, coming through the coil, and then as it's leaving the back side of the lamp. So the 360-degree distribution of energy works really well for inactivating pathogens. If you're not familiar with it, you should be familiar with them. They're the ASHRAE position documents. The ASHRAE position documents specifically talk about there was 2 of them. They just expired, the one on the left, but the one on the left's been around since 2014, and it talked about ASHRAE's position on airborne infectious diseases. And then the one on the right is the newest one, called infectious aerosols. Good to know. This is your society's American Society of Heating, Refrigeration, and Air Conditioning Engineers positions on what you should be doing to be able to mitigate infectious disease. So what are some of the engineering control strategies that you can do? So depending on what you are, whether you're a retail, sports, educational, correctional facility, the very first thing we tell you is to dilute. If you can bring in more outside air, let's go ahead and let's do that. Let's dilute. Can we change our temperature and humidity levels so this virus can't replicate? Wear personal ventilation. We're all wearing masks. Can we exhaust more air? Can we increase our filtration? So that's been a big thing that we've done on the task force, is saying that you should see if you can get if your HVAC systems can handle it, get up to a MERV 13. That's gonna roughly get you about a 40% collection of a 0.11 micron particle as it's going, by just being able to move your filtration up to a MERV 13. Also, can you put upper air UV in? We're going to talk about that in a second. Or what we just talked about, can we put duct and air handling UVGI in? Can we change our flow regimes? Can we change our pressurization? So these are kind of your target things that you should be doing. The infectious aerosols one goes through and talks about, again, UVC being able to inactivate nucleic acids. And the CDC has approved UVGI along with filters for tuberculosis. Be cautious of newer technologies that are out there that are not well documented, well peer reviewed. We've seen a lot of technologies come into the market making claims that are really only manufactured claims. Really no peer reviewed studies out there. So if you're applying something for your buildings, make sure that you're doing what is recommended either through CDC or ASHRAE or the cognizant authorities. So upper room UVGI, you may not be familiar with it, but we're going to take a couple slides and look at it. This is something for more occupied spaces. It is a wall mounted fixture that has to sit up at least 7 feet off the floor. Minimum of 7 feet, can be higher, 8 feet, 9 feet. You still want to be a little bit off the ceiling. You want to be about 6 inches down from the ceiling, as you're seeing this picture here. What these fixtures do is they create this ultraviolet energy and put a very collimated beam above occupants' heads and below the ceiling. So it's taken the natural air currents in the space as your movement is happening, or our supply and our return, where it starts to bring those very small pathogens up into the disinfection zone. So they can be around when folks are there. I keep them, for example, in my office, it's been running for a year, just 24/7 over my desk. So you can be in, like you see on the left, you're seeing kids from a school, it's a college actually, a cafeteria, and then you're seeing an operatory that you'll see some of these. So they're very specific to areas where we want to control contaminants in that space. For example, lunchrooms, cafeterias, places where we have congregate settings. So in fixtures, what you typically see is you have some type of reflector in the back with a bulb, a UV lamp in front of it. So a very high spectral aluminum reflector that will push that energy through non-reflective baffles. So these baffles actually will then keep that beam collimated, where it's only going to be this layer that's above people's heads. So it does not stray down into the space. It's actually this 4-inch beam that just kind of continues across the ceiling. This particular picture you're seeing is by a return. So as the air is coming back from the room through the return, it's going by the highest dose of UV right there. But again, the biggest thing that people get the misconception is they believe the UV is straying down into the occupied zone, and it does not. Well-made products will not allow that to happen. We've been using them we started using them in the 1940s for measles. You can kind of see them in the background here. Was a big epidemic that was happening in schools. So they deployed upper air ultraviolet lights in a space to be able to mitigate it. And we're talking about a coronavirus with, yes, of course, a lot of deaths, but it's nothing compared to the 1.5 million deaths per year for TB around the world. And already 1/4 of the world's population is already infected with tuberculosis. So we started making things back in the 50s called antibiotics and started using antibiotics, but now we're starting to see antibiotic resistant strains of things. So this is becoming more and more prevalent. You saw that in the ASHRAE document. That's one of the very first things you should do to control it in a space. So when you look at, I went backwards, apologize. I wanted to go forward. One of the things that Dr. Shelley Miller did from Colorado State University, she did this up at Harvard School of Medicine, was she was able to go in and look at the outside air rates of what a system would look like when you put, for example, 40 microwatts in. So you're able to achieve air changes per hour to supplement what's happening in that space. So as you increase the amount of fluence in that space, then you're achieving better air quality, and especially if you don't have outside air changes. So they can be put in areas, again, where people are. They can be put into a space like a pre-op. Here they are in a pre-op area. This is a patient's room. It can be on with the patient in there, with the doctors in there running 24/7. I think I mentioned I just keep mine running 24/7 all the time too. I'm sure you're going to have some questions on this, so we'll get those at the end. So then the last thing I want to make sure that you're aware of is that there are, when UV first came out for HVAC systems in the early to mid 90s, we were really actually promoting it as air disinfection devices. Well, in the mid 90s, we didn't have as many folks that could afford to put UV in. It was expensive at that time. So it kind of migrated back to just being a 24/7, 365 coil cleaner, just sitting in and around cooling coils to be able to take out what's growing inside the coil. So we don't want to, with all this pandemic, we don't want to get away from that. We still want to be able to show that this is a good location for us to put UV lights because there's many more benefits. So we can restore coils. Most fins of coils are made of aluminum, so we can actually start to send that UV energy, reflect it down the pack depths, and over a course of a time start to keep coils clean. So as biofilms are growing and just constantly bathing that coil. So they can be, the one on the left is a downstream side of a coil, the one on the right is an upstream side of, the middle is an upstream side of the coil. But typically they're just going to be put on the back side of a cooling coil just to be able to keep them them clean. One of the things we did in ASHRAE a couple of years back is we had a study called Research Paper 1738, where ASHRAE funded a study with a little bit of Department of Energy money, and also the Dr. Bonfleff, his team at Penn State was one who was awarded the project, but they wanted to see what would happen if you just test a system that you're seeing here for an entire year, log every data point you can of how seasonally it worked, and then let's add UV lights in it and let's run them for another year, and let's see what happens with just the application of UV lights on cooling coils. Of course, this was mainly an energy study, but they wanted to do health benefits, maintenance costs, energy costs, all of that kind of stuff were involved in the study as well. So this next picture is kind of to me, it's a pretty dramatic picture, because at the beginning of the study, when they turned the lights on, which would be the left picture, they went to the other side of the coil and said, let's see how much of the visible blue light comes through. And you can see very little. At the end of the study, the picture on the right showed what happened. And so again, it was an energy study. So they saw a 21% decrease in the coil pressure drop, which, you put that into fan brake horsepower formula, you're gonna be able to, most of the time for UV lights going inside of a air handling unit for cleaning them up, they pay for themselves in less than a year, 2 at most. This particular one would have paid for itself in about 6 months. They got a 14% increase in overall heat transfer coefficient. So just a quick review, if we are looking at something that is just going to be for coil irradiation, like we just talked about, what we need to know is what's the height and what's the width of the coil. And that's all that we need to do to be able to put UV lights in that space. Not much different if we need to do something for air disinfection. What I really need to know for air disinfection is now I need the depth. I need the depth of the coil. So this space, this box, and I just need to know temperature, airflow, and those things right there go into a math model that you can calculate out how many lamps that you need for that space. So one of the things, just in summary, UV's been around for over 100 years for water treatment. It's been 80 years for upper room, applying those in the 1940s. 30 years of proven induct applications. We have 2 handbook chapters, both the applications and systems and equipment handbook. 2 test standards that I myself can go send my product to a test lab to be tested against these 2 standards. 3 position documents. Again, it's now going to come down to 2 now that the infectious aerosols is overwritten there. Extensively peer reviewed. It's been around for a very long time. There's multiple peer reviewed studies of what it can do and what it can inactivate. And just remember, there's not a lot of other technologies that are well researched and validated. So these are your buildings with your occupants that you're leasing. Make sure you're putting the right things in there to be able to help mitigate this. So I've got some information here. I also want to throw you real quick over to just a quick area to, all the links will be at the back of this, so you can go to the references that we had on each of the pages. And then if I can, I'm just going to show you real quick another source for information. If you get an opportunity to go to the ASHRAE website, it should pop up here in just a second. So on the ASHRAE website, you have a COVID-19 task force. There's 155 folks, volunteers that are putting together multiple sections of this, and we've got some great information for you, especially building owners out there. As you scroll down, you'll kind of see the different areas: reopenings, buildings, filtration, disinfection, transportation, resources. So the task force that I'm partnering on here is the filtration and disinfection. So if you click on that, it will take you down to our PDF, which is a PowerPoint presentation of different technologies. As you see, we can kind of just go through each of these down here. Air disinfection for UV lights, bipolar, ozone, different things. We have comments on each of those. So it's a really good source for you to be able to go and find some information on. So again, it's ashrae.org, and then look for the COVID-19 link, and you can get a lot of information. I appreciate that. Let me switch it back to the PowerPoint presentations in case I need to go back to it. There we go. Hold on. We're to this one. And let's open it up for some questions. Did we get any text that came in?
We just had one question about handout
here.
And I did let them know that we would go ahead and add it.
There we go. Yeah, so one of the questions from Samantha was, will we have access to the slides afterwards? Yes, BOMA will go ahead and they're recording this, so can have the access to that. I guess you already answered that. So any questions? I'm going to go ahead and open it up to the audience. Do we, Tyler, how do we do that? Guess we can unmute all
One Q&A question, asking for contact information.
attendees. Do you have any questions at all?
And I'd be happy to.
So one quick thing is how long do the UV bulbs last, or how often do you have to be changed? So it's a really good question. So the lamp manufacturers who make them, like a Philips, an Osram, a GE, or the custom guys, give you a 9,000 hour warranty on the lamp. So the lamp is good for, from a warranty standpoint, 9,000 hours. So most folks just change them out at the 9,000. But it really is going to depend on your project. For example, if you're just doing coil maintenance, you can go a lot longer with those lamps. If you're trying to do air disinfection, we recommend that you just change them out per the manufacturer's recommendations, which is going to be 9,000 operating hours. Again, it's operating hours. So if your building is going to go 12 on, 12 off, now all of a sudden that makes it a 2-year lamp. If you're going to do just coil maintenance and you're going to let it go on longer, you can even go 3 years with the lamps. There's a certain point where you don't want it to go too long or it burns the ballast out. So, but we typically say in our ASHRAE handbook, 1 year is best practice. But just like warranties in our cars, that the 3-year, 36,000 mile, your car's still going to go on beyond 3 years. So if it's not critical, change them out 18 months to 2 years. Thank you for that question. Any other questions? That was the last one from Michelle there. Let's see.
There's one on the Q&A portion of the dashboard there, Dean.
I don't see anything else come up here. Tyler, do you want to jump on and say anything?
Apparently can you not hear me, Dean?
My apologies. Yeah, I'm here.
Okay, I'm not sure if my audio is working. We do have 1 or 2 Q&A questions in the dashboard. I answered one as far as providing my contact information.
Perfect.
We at Mechanical Sales are the local representative for UV Resources, so we'd be happy to answer any additional questions, come out for walkthroughs, make presentations, really do anything we can. We're kind of the boots on the ground resource for UV Resources here in Kansas City. Dean is obviously available for support and helps us a great deal in making sure we're taking the proper approach and sizing the equipment right way. But yeah, I will provide my contact information on the Q&A here. Happy to help however we can.
I think you guys may have been asking questions and my speakers were acting up, but they're working now. So apologize if somebody still had another question other than through the chat. Great. You'll have a copy of this and all the references there. I've got my contact information. Tyler's our local local source there. I hope this was helpful for you. Certainly use Tyler, use this presentation, go to the ASHRAE website, make sure you have some good information. And if you have any questions whatsoever, just certainly let us know.